fish, don't let it get away. If you lose it, just scan the band. Run every frequency you can think of.
So what I want to talk to you about today is the coolest technology that was invented in the past 200 years. At the same time we have discovered how to wirelessly communicate across the globe, we simultaneously discovered how to do it at the fastest speed possible. And that is through radio. Radio travels at light speed as electromagnetic radiation, and we use it to communicate between our laptops and our routers. We use it to reach out and send messages to the stars, and we also use it to listen. One of the biggest radio telescopes we had, we unfortunately lost. It was the Arecibo telescope, and that is one we actually used to transmit a message to the stars. What I want to talk to you about today is radio and amplitude modulation. Amplitude modulation is going to lead us into talking about Hilbert spaces and some kernel methods. And yeah, why don't we go ahead and get started. Today, I want to talk to you about AM radio, carrier frequencies, resonance, and how resonance is a lot like projection in a Hilbert space. And then what we're going to do is we're going to make a kernel function. This kernel function is going to emulate the way that an antenna uses resonance in order to extract an amplitude modulated signal, and we're going to make this kernel function to extract an amplitude modulated signal out of a whole collection of different signals, just like what we would see at the typical EM spectrum. Before we start, why don't we just talk about what amplitude modulation is? So amplitude modulation is one of these early technologies that allowed people to broadcast signals over a very long distance. So we're going to have a single sinusoid whose frequency is what we call the carrier frequency. This is typically a very, very high frequency signal that we're going to then modulate by adjusting the amplitude. And by doing this adjustment, we can go ahead and we can encode a signal that we want in some sort of audio signal that's coming from a microphone, or maybe a musical signal of some kind, or even a digital signal. And we're going to go ahead and hit the amplitude of the carrier sinusoid with this new signal that we care about. And this is more or less how amplitude modulation works. There's a couple of things that we do want to adjust for. First of all, one thing we're going to do with the signal that we're trying to send is we're going to sort of shift it up, and so do sort of this baseline shift, and then we're going to multiply against the carrier frequency. And this way the carrier frequency never completely vanishes, and so which makes it easier to detect. Now, amplitude modulation was invented roughly around 1900, and it became popular in regular homes in around the 1920s. People from the 1920s say that we cannot conceive of what the world was like before AM radio came in, where you had households that were sort of isolated and quiet, now suddenly having the whole world coming into the living room. This is a lot like the transition in the 1990s, before and after the internet, where suddenly you can chat with people from all over the world. Amplitude modulation was a lot like this, where you have musical stations playing in your living room, you have people coming on and talking, you have the news coming straight to you, being told to you by a person you have never met. This was a complete revolution in the whole way that we communicate and take in media. These sort of advances were so important that in 1909, the Nobel Prize got awarded to two people who helped push forward radio transmissions and long-distance wireless communication. This is Guglielmo Marconi and Carl Ferdinand Braun, and this was in 1909, and this was the Nobel Prize for Physics, cited as being in recognition of their contributions to the development of wireless telegraphy. I find one of the more informative videos on the internet that explains AM radio, and in fact even the difference between AM and FM radio, is this video from the military, the US Army, back in 1964. And there it's a black and white movie that sort of goes at a nice slow pace, explaining exactly what AM radio is, what it's sort of sensitive to, it is very sensitive to noise, and why FM radio is better.
Let us review in detail the separate actions which take place in an AM transmitter. The information or intelligence to be transmitted starts as sound waves which travel through air.
Now, I'm not here to talk about the merits of AM radio versus FM radio. What I really want to talk to you about is projections and the resonance idea behind AM radio. So let's talk about what amplitude modulation does to our signal. Essentially, we have a carrier wave that is supposed to carry our signal. And so we multiply a new signal that we want to transmit times its carrier wave. So if you think of a signal that you're trying to transmit, and we know that signals can be encoded as a collection of sinusoids, sines and cosines of varying degrees, we can go ahead and take our signal that we care about, and after doing this whole baseline shift and maybe a little bit of scaling, and multiplying by the carrier sinusoid, then we can see what happens to the frequencies of that product. Essentially, there's a few trigonometric identities that we can use in order to show that the result is going to be a whole collection of sinusoids that are basically the carrier frequency, but shifted up and down by the frequencies of the other sinusoids that we multiplied by. So what ends up happening then is that we have this whole width of frequencies that are centered at the carrier frequency. And so this allows us to have an area where we can isolate in sort of this a spectral sense, or later it's going to be a Hilbert space sense, around the carrier frequency. And so if you have another carrier frequency with its own multiplication of a signal, that can, as long as it's far enough away from the original one, that should not interfere with the signal that we care about. And this is pretty much the principle behind AM radio, and why you can have all these different overlaying broadcasts in the same region, all with completely different signals that get to your radio. Now, how does it get to your radio? How does your radio know to pick out one signal versus another one? And this is the idea of resonance. Essentially what's happening is that there's a circuit inside of your radio that tunes the resonance of your gigantic antenna that you have coming out of your car. So then this antenna is tuned to resonate in a region around your carrier frequency. And so essentially, it gets moved like a giant electromagnetic sail being hit by this carrier sinusoid with the signal that you care about. And then you put that vibration into your speakers, and then you hear the radio. This is a very simplified view. I'm not an engineer or radio engineer at all. But this is, in principle, exactly what's happening. And what's interesting here is that we can take this idea of resonance and think of it as sort of a projection in a Hilbert space. If you don't know what Hilbert space is, don't worry, we're going to walk through this one step at a time, and there's a link at the end of my video that will connect you to a further Hilbert space lecture that I did last year. Okay, so first thing we're going to need to talk about in order to isolate the signal using a mathematical method is to talk about orthogonality. Here, we're going to use it in a sort of signal processing context. So what we're going to do is we're going to restrict ourselves to the interval 0 to 1, and we're going to take a look at sinusoids of varying frequencies. So for instance, if I take the product of, say, sine of 2 pi nt times sine of 2 pi mt and integrate that dt, then ultimately what that's going to end up giving me is I can use a cosine sum identity, and I can show that this integral is going to be 0 if n is not equal to m. And if n is equal to m, we're going to get some constant out of it. It's going to be the same constant for every single one of them, so we'll be able to divide it and sort of normalize, so we just get a 1 out of that signal. I don't remember off the top of my head. Probably it's like 2 pi or something like that. Now, the same thing happens if you have cosine of 2 pi nt times cosine of 2 pi mt, and also sines times cosines, and all of these integrate to being 0 if n is not equal to m. So this concept is called orthogonality, and when we divide by that constant 2 pi, you ultimately end up getting what is called an orthonormal basis. So these are a collection of functions that can describe any sort of signal that we want, and using sines and cosines through what we call this inner product. And we can sort of isolate one particular frequency out of a signal by multiplying that signal by sine of 2 pi nt, for instance, and then that's going to extract the coefficient that goes on the sine of 2 pi nt inside of the signal itself. So we can use this idea to rip apart a whole collection of signals that are sort of overlapping, and we can extract exactly the signal that we want. And this is what resonance is doing on the physical level when it's extracting an AM signal using resonance at the carrier frequency. So what we're going to be thinking of is that we have a whole array of different frequencies, and they're going to have whole groupings of overlapping AM signals, some having the signal that we want and other ones having signals that we want to ignore. And so what we want to do is we want to isolate that one smaller group of signals, and it's going to give us what we call a subspace. So what I'm going to do is I'm going to ultimately develop what we call a projection from the larger space down into this subspace, and we can implement this using what we call a kernel function. So we're going to construct something called a kernel function using all these sinusoids. We're going to slap them together. And so we're going to think of our whole array as being a collection of sinusoids, and we're going to cap off the highest frequency somewhere. So why don't we go ahead and start at sort of the one-dimensional level. Let's say we're looking at only our carrier frequency. So we have some sort of carrier frequency, we'll call that f sub c. And so the sinusoid that this is attached to is sine of 2 pi f sub c times t, right? F sub c is some integer, really, really big, something like 10,000, 20,000, something like that. We want to be able to extract the coefficient that goes on that guy in particular. So let's say we just have a really, really simple signal that is just constant. So we multiplied this carrier frequency by something like A. Now remember, we have a whole bunch of other signals that we want to ignore. And so what we get coming into our sort of mathematical radio is all these overlapping signals, and we want to get rid of all the ones except for the one that is our carrier frequency with the constant A on it. So what I can do is I can take that broader signal, let's call this like capital Y, that contains all of the signals, including the ones that we don't care about. And we were going to take a look and see how to go ahead and project that. So what we do is we take that Y of t and we multiply it times sine of 2 pi f sub c of t, and then we take the integral from 0 to t. And what that gives us is it's going to give us a. Well, 2 pi a, but remember we're trying to divide by that normalization constant. So it should give us a at the end of the day. But that's just a constant function, that's not actually our signal. So I want to be able to get a signal out of this. And so what I can do is I can multiply by something else. And so I'm going to take this y of t, and I'm not going to just integrate it against this sine of 2 pi f sub c of t, but I'm also going to multiply that term by a constant that has a variable in there called s. And so this is going to be sine of 2 pi f sub c of s. So this other term doesn't involve t, it can even be factored out. And so then when you go ahead and you take that inner product, what you ultimately end up getting is a times sine of 2 pi f sub c of s. And so now you have your signal, the constant signal that you sent in with your carrier frequency, now that is just written as a function of s instead of t. And so this is sort of your first kernel function where you're using what we call the reproducing property. So essentially, we have a function of two variables, t and s, and we'll call this k of t comma s, and this is equal to the sine of 2 pi f sub c of t times sine of 2 pi f sub c of s. And when you take the integral of 0 to 1 of y of t times k of t comma s, the result is that you end up getting a function of s. And in particular, we've projected out the term that we care about out of y, and so this has also enacted a projection onto a one-dimensional subspace. So how do we get all the other ones? Generally speaking, our signal is going to be composed of, a range of frequencies. So what we want to do now is we want to develop a kernel function that is going to have a range going from, say, minus 500 below our carrier frequency to plus 500 above our carrier frequency, and we're just going to take every integer from the carrier frequency out and include those. And so what we can do is we can just exploit linearity of the inner product and just do this one at a time, and we reassemble them. And so essentially what we're going to do is we're going to build a kernel function just like this. So it's going to be, say, sine of 2 pi times f sub c minus 500 t times sine of 2 pi f sub c minus 500 times s, and then adding all of those up until you get to f sub c plus 500 in each of the terms. And then, of course, we also have cosines that we need to worry about, so we'll throw those guys in there too. And there you go. You have a kernel function that'll extract exactly that sort of frequency content that you want. When you take this kernel function and you multiply it by our whole field of our sort of, quote, electromagnetic spectrum, and then you take the integral from 0 to 1, and then you get exactly that chunk of the spectrum that corresponded to the original signal that you use amplitude modulation for. If you try to play this back, you're going to have that carrier frequency sort of getting in the way. And so if we actually take a look at the spectrum that you get out of using AM radio, you can see that your spectrum that would usually be centered around the origin has now been shifted to be centered around the carrier frequency. So then we need to shift that back. And then after you've done those two operations, then you're done, and that gives you your original signal back that you have transmitted using AM, and then you take it back in, you've shifted it over, and then of course we need to do that baseline correction again, and then you can sort of remodulate it using the volume after that. But that's your signal, and you've extracted it using what is called a reproducing kernel. So this is what is going to be called a reproducing kernel for the subspace that corresponds to our AM frequency. So we can call this, if you'd like, our AM kernel, but it's usually called a Fourier-based kernel. And so by accounting for the frequencies below and above the carrier frequency, what this is talking about the double sideband, hold on, I always need to look this up, the double sideband amplitude modulation. Well, I guess that wasn't actually much to look up. But in any case, that is like the early version of AM radio that was popular back in the 1920s. And so now you know how to handle this thing with a kernel function. Now, this uses the reproducing property of a kernel function, and this is sort of one of the defining features of a kernel function. And now at the end of the video, I'll give you some links to take you back to talking about Hilbert spaces, reproducing kernel Hilbert spaces, and a lot of the theory behind it. But before we leave, I'm going to go ahead and do a MATLAB example and walk you through exactly how we can do this sort of setup and see if we can actually get this working with some very simple signals, but we'll set up a whole bunch of different sort of AM signals, and we'll see about extracting it using this kernel function that we just described. Okay, so with that, I'm going to go back to my office and we'll do some coding. Okay, so I went ahead and made up this whole kernel code, and essentially remember we have a kernel function that is a sine of particular frequencies as a function of t pairwise multiplied by sines of the same frequencies as a function of s. And so this kernel function is a function of two variables, t and s, and we're going to use this as a projection operator to look at a field of simulated electromagnetic signals that are sort of overlapping each other. We're going to extract exactly the one we want. And so all of these have carrier frequencies that are distinct from one another. And so we're going to have carrier frequencies at, say, 100 hertz, 150 hertz, and 200 hertz, carrying signals that are, say, at most 15 hertz. So let's go ahead and take a look and see what we have. So in here, I'm just putting together these signals, and so my time domain window I'm making from 0 to 3, and I have my signals in here. These are my carrier signals, YC1, YC2, and YC3, and they're respectively 100 hertz, 150 hertz, and 200 hertz. We can go ahead and plot them, and it's not going to be that big a deal. Doop. And there we go. You don't really see much going on here. If we zoom in a whole lot, you can start picking out some of their frequency, some of their periods. But otherwise, they're so high frequencies that they just look like a solid mass. And so not a lot to see there. So now we have our modulating signals, and so these are signals we're going to be attaching to our carrier waves. And so there are three different signals in here, and we can go ahead and zoom in on a bunch of them. And so you see there's a blue one, a red one, and a yellow or orange one. And so these are the modulating signals that we're going to put on top of our carrier waves in order to transmit the signal. And so then this is what we do. We go ahead and we take that signal and we normalize it, so we make it pretty small in amplitude. That way that the carrier signal ends up never being killed. And so you're not going to get 0 out of this, for instance. And we shift it up by 1. And yeah, so then we have these guys. So these are our modulated signals. If I go ahead and do this. And so there you go. So yellow, red, and blue, these are my three modulated signals that we're going to be using as sort of our simulation of amplitude modulation. Now, the idea is that we're going to add all of these together into something that we're going to call the full sum. And so this takes mod y, modulated y1, modulated y2, and modulated y3, and adds them together. And I don't think I've plotted that yet. I can go ahead and do that. So we can go ahead and say figure and plot t and full sum, and let's see what we get. And so this is what you're getting. And so it doesn't look like any of those signals that we saw before, and is sort of just everything stacked on top of each other. And so we're going to use a kernel function to act as a projection to extract exactly the one we want, and this is going to be the one that corresponds to 150 hertz. Now, obviously, you're going to be dealing with much higher frequencies in the real world because you need to make sure that your space, that the carrier frequency is going to be much, much larger than the thing that you want to transmit. And so, since you're often going to be transmitting, voice and amplitude modulation is used for talk radio, then you're really going to want to be somewhere around your actual signal that you're modulating with is going to be something around, say, 300 hertz up to maybe 1,000, depending on how old you are and whatnot. Children are several octaves higher than an adult. And so, so anyway, so this is the full sum of all three of those modulated signals. So I make a kernel function, and so I have the carrier frequency at 150, and I want each one of the sinusoids ranging from underneath 15 underneath the carrier frequency and up to 15 beyond it. And so I sort of put these guys together. So if you take a look at this, basically these are the frequencies that we're going to be running through. And so that's what this little bit enacts. And then I multiply that by TT, which is my variable here. I didn't want to confuse it with T from earlier. And then I multiply that, and then I put 2 pi on it, so I make sure that it actually is the frequencies that I'm thinking of, and then I hit it with sine. And so that's going to end up giving me a row vector, which is basically sine of all these guys times t, roughly. So now I'm going to take a row vector of the same exact thing, but with s, and then I multiply them together, and this basically gives me a sum of all these pairwise multiples of the sinusoids. And then I do the same for cosine, and that makes sure I pick up everything. And so, so that's not too bad. Then I make up this variable integrating, and this is going to be the signal I'm extracting from here. I said integrating because I'm doing this integral in order to do the projection. And so the signal itself, so we're going to integrate with respect to t of j. So that's going to be this first variable here. So it's with respect to t as far as this is concerned. And s is going to range, otherwise it is going to be stepping through and being our variable. And so basically for each s, which is coming out of here, I do this integral with respect to t. And then I input it into this guy that I call integrating, and then I move on to the next one. And so this basically is a function of s now, but symbols don't really matter. Okay, divide by this just to normalize it down. I mean, it doesn't really matter where you're going to get it. It's just going to be a scaled copy, and at the end of the day, if you're receiving this on a radio, you're just going to tune it with the volume one way or another, so not a big deal. But just to keep things sensible, we divide by this. And so let's go ahead and see what we get. So this is going to take a few seconds to get out of here. So let's go ahead and do that. So it usually takes about 30 seconds or so to put together. Mainly it's because I have a double for loop, and there's a lot of sample points. I'm sampling about 1,000 per second. But yeah, I mean, at the end of the day, I didn't want to make it too complicated, and I wanted to get this done rather than being too efficient, and 30 seconds isn't the end of the world. So let's go ahead and do that here. And if you're going to want to do this for more data points, there are definitely faster ways to go about this. Okay, so this gave me 4 different plots now. Let's see. So we have the original signal here, and then this is the modulated carrier signal that we threw in, and then when this is what it looks like when it's slapped together with the other carrier signals, and this is what you get after you do the integration. And you see that these guys are practically the same. The original modulated carrier signal is only going up to 1.5, and this one goes up to about 2.5. That's fine. Like I said, the amplitude doesn't really matter all that much here. We can tune it later if it's too big. And so yeah, so that's the projected signal. And so now what we want is we want to be able to get back this original signal. And so let's go ahead and see how we do that. So first, let's take a look at the Fourier series, or the Fourier coefficients, the frequency domain. And so, so let's go ahead and take a look in here. Not to give away the end, but that's that. So essentially, this here shows us the spectrum of the full sum, all three of them together. And you see that this guy corresponds to the 100 hertz, this guy corresponds to the 150 hertz, and this corresponds to 200 hertz carrier frequencies. And this guy is what you get after you do that integration. So I did a Fourier transform of the projected version that I got, and you see that only the 150 hertz ended up surviving here. So this guy survives, but the other two dropped out, and that's just from integrating against kernel. So the kernel function essentially did a bandpass for us, and that's really handy. Now, if you want to be able to get the original signal back, well, I mean, the original signal is now, the frequency is centered around the carrier frequency. You want to be able to get this back to 0. And there's a really cool trick that you can do. And you basically multiply your modulated signal by the carrier frequency again. And what that's going to do is it's going to multiply, so since I'm multiplying by a sine of basically the carrier frequency, we're going to have an exponential of plus I times the carrier frequency of t, and then we have the minus I version of that. And so when we multiply that together, it's going to shift these two guys back together in one case, and so it's going to slam these two together, and then it's going to also shift them out back and front. So we're going to have three chunks now. We're going to have one that goes out here, and two that come in here, and one that goes out here. And so, and then all we need to do is we need to do just a little bit of filtering, and we can extract the signal. And so, what we end up getting then is, let's see, do I have the Fourier transform of this guy? Yeah, let's go ahead and show you what you get when you do that multiplication by the carrier frequency. So, let's see, so I'm going to make a figure, and now we're going to plot, say, f against this. And by the way, all of this Fourier transform stuff that I'm doing here, this is the same code that I used for the time grapher. All right, so let's go ahead and plot this. And so you see, that's exactly what happened. We now have guys at 300, and before we had 150, and then we have two of these guys at around the origin. And what's really slick is if I now zoom in on this, we have a peak around the -10, a peak at the 5, and a peak at the 3, and then 1 at 0. The 0 is coming from the fact that we added 1 to our modulated signal. And then otherwise, signal 2 has a 5, a 10, and a 3. That's exactly the signal that we wanted. So now let's go ahead and see what we get when we take a look at the recovery. And so here, and this looks practically identical to the original signal. It's one of these figures here. Not that one. There we go, original signal. And so these two guys are practically the same. The scaling factor, again, is a lot different. The original signal got really, really big, but again, we rescaled this guy a bit and shifted around. And this isn't centered at 0 anymore, but I mean, we can always move it back down by just looking for the average. But yeah, there you go. We recovered the signal. And now we just need to do a little bit of shifting, and that's no big deal. And yeah. So that's basically what you can do with kernel methods. We made an amplitude modulation kernel that extracted exactly the terms that we wanted out of a whole collection of overlapping amplitude modulations. And so it acted as a projection onto a subspace, and then we used the S variable in order to actually make this signal here. Now, we did use a little bit of filtering at the end of the day in order to extract exactly what we wanted, the signal from the amplitude modulated bit. But yeah, that's that. Okay, so thank you for sticking in here with me, and I think I'm going to call it. All right, so please subscribe and tune in for more about kernel functions, because that's pretty much going to be the rest of this class. All right, gonna go, and thank you for watching.